Hello, welcome to NPTEL online certification course on Introduction to the Application of AI to Robotics. Today we are going to discuss about the Cartesian-based control systems. So, the learning outcome for this lecture is your understanding on Cartesian-based control system and how do we implement that Cartesian-based control that you will be able to understand. So, if you look for the content of this course, it consists of comparison with the joint base scheme, then intuitive scheme of the Cartesian control, Cartesian decoupling scheme, and then finally I will close with the adaptive control scheme. Okay. So, we have seen the joint base scheme in detail. Okay. So, these joint based control systems, how they were done? There we were basically calculating say the error in the joint position, joint velocity and joint acceleration. Okay. And you see in many application we want end effector to move along a straight line, okay, or say follow path in workspace coordinate or track trajectories directly in the Cartesian space. So, from this actually the requirement of the Cartesian control comes. Okay. So, let us look at the key concepts. So, here in case of Cartesian control, what we are doing essentially, instead of controlling the joint angles theta directly, we are controlling the positions, okay, end effector position in the Cartesian space. Okay. You see the traditional joint base schemes require the trajectory conversion, okay, because you see we are always interested in moving the end effector in a desired way, right, based on our requirement. So, the traditional joint base scheme consists of something like this, okay. So, what you have an arm and from that arm you get a theta, right. And you see we know the desired Cartesian position, Cartesian velocities and the Cartesian acceleration. These information we send to the trajectory converter and this trajectory converter in turn gives us the joint position, joint velocity, joint acceleration. So, from the arm I get the theta value. I am not showing the other values, that is theta derivative as well as theta double derivative. Okay. So, it comes to the comparator and we get the basically the error, okay, and then it is multiplied with the gains and we get the torque. So, this is what is there in the joint base control scheme with Cartesian path input. Why Cartesian path input? Because I am supplying the Cartesian position, velocity and acceleration over here. Okay. So, you see these Cartesian trajectories must be converted into the joint trajectories, and how can we do that? That we can do using the inverse kinematics. Okay. So, the joint base control with the Cartesian input, you see the desired Cartesian trajectories must be converted into joint space quantities as we have seen in the previous block diagram. So, what are the requirement? How do we do that? So, this value, that is the joint position vector, I can get from the inverse kinematics, alright. So, if I know the end effector position and orientation, then I can get the through inverse kinematic the joint position vector, okay, and the desired joint velocity I can get using the Jacobian inverse, alright. So, this concept we have already covered in our earlier lectures, and in order to get the desired joint acceleration I can take the derivative of this equation, right. So, this is what I get, okay. Now, what is the problem with this approach? It is computationally expensive and it requires Jacobian inversion, okay. And problem with Jacobian inversion we have already seen, the singularity may occur, okay, and the numerical differentiation amplifies the noise and it also introduces the delays, okay. So, instead of converting Cartesian trajectories into the joint trajectories, we compute error directly in the Cartesian space, right. So, can we do that? Yes, using the direct Cartesian space control. Okay. So, here we get the Cartesian error directly, where my xd is the desired end effector position and x is the actual end effector position. Alright. So, how does the block diagram looks like? So, it looks like something this, say you have the arm, you get the joint position, alright. Use the forward kinematics in order to get the end effector position, okay. And here you have the desired end effector position, alright. So, we send it through comparator, we get the error, and then we could have the coordinate conversion and the gains, okay. And from that we get the torque, and that torque drives the arm, okay. So, this is how this is possible. Then there are advantages and challenges of the Cartesian control. If you look at the advantages, direct control of the end effector motion, that is possible here. It is easier straight line trajectory tracking, and the desired motion can be specified naturally in terms of the workspace coordinates. Alright, we could have the position as well as orientation as well of the end effector. Now, coming to the drawback, you see the kinematic computation moving inside the control loop requires coordinate conversion, Jacobian calculation, and the inverse transformation, and this puts a higher computational load. So, that is the drawback here. Okay. Next, let us look at the intuitive scheme of Cartesian control. There are two intuitive schemes possible. One is what we call as the Inverse-Jacobian controller, and the other one is the Transpose-Jacobian controller. Okay. Both methods try to reduce the Cartesian position error, right, and generate joint torques that moves the end effector towards the target. The key idea here is that the Cartesian error must somehow be converted into the torque, alright. So, how we do that? Let us look at. So, first we begin with the Inverse-Jacobian Cartesian controller, okay. So, here in this case you have the arm here, you get the theta, you have the say forward kinematic relationship, you get the Cartesian position and orientation, right. From here you have the desired Cartesian say position, orientation, okay. You get the error. Now, we multiply this with the inverse of Jacobian in order to get the error in the joint trajectories, okay. And then we multiply it with the gains in order to get the joint torque, okay. So, the control principle is, as I said, the Cartesian error is converted into the joint displacement correction, and then using the inverse Jacobian we can get this relation, okay. And again we can apply the gains to generate the torque, okay. So, basically it tries to find which joint motion will reduce the Cartesian error, okay. Next, let us look at the Transpose-Jacobian Cartesian controller. In this case, you see the control principle is that the Cartesian error generate a virtual Cartesian force, okay, and this force is mapped into the joint torque using the Jacobian transpose. The control flow here, what we do, we compute the Cartesian error, okay, and then generate the Cartesian force and then convert the force into the torque, okay. So, in case of the transpose Jacobian, so you have the arm here, you get the theta, right, use the forward kinematics to get the end effector position and orientation. Here you have the desired position and orientation coming, then here you find out the error, you multiply with the gains, okay, this one, okay, to get the f value. And once you have f, we multiply with the Jacobian transpose here in order to get the torque value, okay. Next is the Cartesian decoupling scheme. You see, in Cartesian control, errors are expressed in workspace coordinate, okay, because we are dealing with the Cartesian control. Now, the goal here is to obtain uniform Cartesian tracking performance, and which is independent of the manipulator configuration. Okay, and what desired behavior we want basically, as with other systems which we have seen, we want the critically damped system, right, fixed closed loop dynamics as well as the decoupled motion. Okay. So, if you look at the Cartesian space dynamics, the manipulator dynamics can be written in Cartesian coordinate as this one. In the previous lectures, we have seen these equations actually, right, and this equation is written in the Cartesian form, right. It is analogous to the one which we have seen for the joint space. Okay. So, in this one, your F is the Cartesian force or moment vector, mx theta is the Cartesian inertia matrix, chi is the Cartesian vector which is basically the position and orientation of the end effector, and this is Vx theta theta dot is the velocity dependent term basically which contains the Coriolis and the centrifugal components, and you have the gravity term. Okay. So, this is the joint equivalent form of what we have written here in the Cartesian one. Alright. So, in this case basically here you are shown with a manipulator, simple manipulator, right. So, here are the Cartesian position and orientation of the end effector are specified, okay, this one, alright. Okay. Next is the model based Cartesian control law. You see, we use Cartesian dynamics to achieve what? We want decoupling, we want linearization, we want fixed Cartesian dynamics. Okay. And to compute the desired Cartesian force, okay, using the model based controller, okay. So, this could be our model based controller. Okay. Alright. So, this is what earlier also we have seen during the partition based controller. Okay. So, here F dash is the servo law component. Okay. The important issue here is we cannot directly apply Cartesian force to the end effector, right. So, what to do? So, to get that desired Cartesian force at the end effector, we have to apply the joint torques. Now, what this torque value could be, that we can calculate over here. So, this is the joint torque which you have to apply in order to get this one, the Cartesian force and moment. Okay. So, your Cartesian model based control scheme looks like something this. So, you have your arm, you get your theta and theta dot, right, from the sensors. Okay. Now, you use the forward kinematic equation here in order to get x, and you use the Jacobian in order to get the x dot. Alright. Now, you have the desired x d dot and you have the desired x. Okay. So, from desired x you get the error vector, and from the desired velocity you get the error in velocity vector. Okay. So, you multiply error in velocity vector with the gain kv, and error in the position vector you multiply with the gain kp. Okay. Add it up here, okay, and here you have the desired double dot. Now, what we do, we have the mx theta here being evaluated. So, for that we are getting the theta value from here, okay, alright, and we also evaluate this v and g values which are the, in the Cartesian space, written in the Cartesian space, right. Now, these values are added up here, okay, and then after they are being added up, what we get is the tip force and moment. Now, we multiply with the Jacobian transpose this one in order to get this torque. Alright. So, this is how this Cartesian model based control scheme is implemented. Okay. So, the Cartesian controller compute the desired end effector force, and the Jacobian transpose converts it into the actuator torque. Okay. And this is our the Cartesian servo law. Okay. That is the F dash. So, if we look at the controller structure, the system contains what? Cartesian error computation, okay, say these one, error in position, error in velocity, model based compensation. So, basically this part, okay, and these parts are the from the model. Then you have the Jacobian transpose block, this one, manipulator dynamics that comes here in the arm, okay, and we have the forward kinematic block, which is this one. So, unlike joint space schemes, the coordinate transformation are now inside of the control loop. You see, if we want to get it practically implemented, the real-time Cartesian model computation is expensive, okay. There are certain issues which arise in the practical implementation, okay. So, what is usually done is that people use the dual rate architecture. And what is that dual rate architecture? In dual rate architecture, basically what we do is that we could have the fast servo loop, alright, and the slower background update of the dynamic parameter, alright. So, this could be done, and the dynamic parameter depends mainly on, you see, the configuration. So, this part is our servo part, as we have seen already, okay, and this part is our the dynamic parameters, okay, which is your mass, and these parameters are the dynamic parameters, okay. So, these dynamic parameters depend mainly on the configuration. So, the manipulator configuration changes relatively slowly. That is why I am talking about here the dual rate architecture, that is the evaluation is done at the different rate, okay. So, the parameter update rate can be slower than that of the servo rate, okay. So, if you look at the advantages of this one, you see we get the improved disturbance rejection, better Cartesian trajectory tracking, and we have the direct workspace control which we have been looking for, right. And if you look at the drawbacks, we have the higher computational complexity, more coordinate transformations, and the increased implementation difficulty. Next, let us look at another type of interesting control problem, and that is what we call as the adaptive control. Okay. Here the main idea is that, you see, in model based manipulator control, what we needed? We needed the exact evaluation of the parameter MVG, right. So, you need to have the exact dynamic parameter, and that is often unknown, right. That is one of the greatest challenge of the model based control, okay. Now, if the model parameters are incorrect, naturally what is going to happen? We will be having the servo error will be appearing, and the perfect cancellation which we are expecting, okay, for the nonlinear parameters, right, nonlinear terms in the control expression, that may not be possible, alright. So, in model based manipulator, parameter may change due to several reasons. You see, say if your payload variation is there, wear and aging components is there, and the changing center of mass position is there, okay. You may have the frictional changes also, and we may also have the unknown inertia, okay. So, here in adaptive control, what we do is that we continuously update the model parameters. You see, in the previous case, model based control, we were using the fixed model parameter, okay. So, that problem is now overcome by continuously updating the model parameters, okay, and reducing the tracking error during operation. And this allows the controller to learn system dynamics, okay. And instead of using fixed parameter, the controller estimates these parameters online and updates the dynamic model automatically, okay. So, this is what is done. So, here basically you have the arm, you get theta and theta dot from the arm, you have the desired value of theta, you have the desired value of theta derivative, okay. So, here you get error in the joint velocities, and here you have error in the position, okay. Now, in the servo part, we have the same thing, that is KB, KP being used over here, okay, and theta d double dot here coming from here, tau dash is here, okay. So, from here we take your error vector, this one, okay, and you take error derivative vector. It is given to the adaptation laws, okay, and from here we continuously change these dynamic parameters over here, okay, in the dynamic model. So, the controller structure, what all we have? We have the servo law controller and we have the dynamic model. and we have the adaptation mechanism. So, this is based on basically your servo portion, this is your dynamic model portion, and this is your adaptation law. Okay. So, to summarize, in this lecture we studied the concept of Cartesian-based control system and compared them with the traditional joint space controller. We learned how control trajectories are converted using, say, inverse kinematics, Jacobian transformations, coordinate conversion methods, right. Explored two intuitive control schemes. One was that of the inverse Jacobian and another one was the Jacobian transpose, right. And we introduced the Cartesian decoupling and model based control scheme using Cartesian space dynamics and Jacobian transpose torque mapping. And then we finally discussed the adaptive control law, where we are changing the dynamic model parameters, okay, continuously rather than using the fixed model parameters, okay, and that improves the model behavior. Okay. So, this is the reference J. Craig, you can refer for this lecture, and thank you.